Welcome to session 3 with focus on risk tolerance and asset allocation. We will also cover passive strategies in combination with the capital market line. The learning goals for session 2.3 are: you should be able to explain the utility maximization problem as a function of allocation to the risky asset Y. You know what and how non-normally distributed returns impact the allocation to the risky portfolio versus the risk-free vehicle. And students should be able to explain passive strategies in combination with the capital market line. Risk tolerance and asset allocation. From the previous session, we have learned that the expected return of the complete portfolio is a function of its standard deviation, resulting in a straight line called the capital allocation line, which is defined by the intercept RF and the slope, which is the risk premium divided by its standard deviation. This is also called the Sharpe ratio or reward to volatility ratio. We have also shown in the previous session that the standard deviation of the complete portfolio is the standard deviation of the risky asset multiplied by the risk portfolio proportion Y. Therefore, the variance is simply computed by the square of the standard deviation. Utility levels for various positions in risky assets. We have shown how to find the capital allocation line, the graph of all feasible risk-return combinations available for capital allocation. The investor confronting the capital allocation line now must choose one optimal complete portfolio C from the set of feasible choices. This choice entails a trade-off between risk and return. Individual differences in risk aversion lead to different capital allocation choices. The goal is to maximize individual's utility function. In the table below, this is found at y equals 0.4. For an investor with a risk aversion of 4, where he achieves the highest utility. Utility as a function of allocation to the risky asset Y. Continuing from the previous slide, this graph shows that utility is highest at y equals 0.41. When y is less than 0.41, investors are willing to assume more risk to increase expected return, but at higher levels of y, risk is higher, and additional allocations to the risky assets are undesirable beyond this point. Further increases in risk dominate the increase in expected return and reduce utility. Continuing on the previous slide, the question is there a way to calculate directly the best possible allocation Y to risky assets? Yes, we can solve the utility maximization problem more generally by using the general utility function. As a next step, we replace the variance of the complete portfolio with the following term: y squared times the variance of the portfolio. To find the maximum, we use the first order condition, resulting in the following formula, which equals to 0. Solving for y gives us the optimal position for risk-averse investors in the risky asset Y. This solution shows that the optimal position in the risky asset is inversely proportional to the level of risk aversion and the level of risk, and directly proportional to the risk premium offered by the risky asset. Calculation of indifference curves. A graphical way of presenting decision problems is to use indifference curve analysis. To illustrate how to build an indifference curve, consider an investor with risk aversion of A equal 4, who currently holds all their wealth in a risk-free portfolio yielding 5%. Because the variance of such a portfolio is 0, we use the following equation, which would result in an expected return of 0.05. Now we find the expected return. The investor would require to maintain the same level of utility when holding a risky portfolio, say, with a standard deviation of 5%. Using the formula would apply that the necessary expected return increases to 0.055. We can repeat this calculation for other levels of standard deviation and other levels of risk aversion, resulting in 4 indifference curves shown in the table below. From the previous table, we can plot the indifferent investors' indifference curves. Notice that the intercept of the indifference curves are at 5% and 9%. This is exactly the certainty equivalent return corresponding to the two curves. Any investor would prefer a portfolio on the higher indifference curve with a higher certainty equivalent return. Portfolio on the higher indifference curves offer a higher expected return of 4% for any given level of risk. The graph also demonstrates that more risk-averse investors are on the steeper indifference curve compared to less risk-averse investors, which are on the flatter curve. Steeper curves means that investors require a greater increase in expected return to compensate for an increase in portfolio risk. As a next step, we can identify the highest possible indifference curve that still touches the capital allocation line. The resulting tangency point corresponds to the standard deviation and the expected return of the optimal complete portfolio. The graph reveals that the indifference curve is U 0.08653 is tangent to the capital allocation line. The tangency point corresponds to the complete portfolio that maximizes utility. Expected returns on 4 indifference curves and the capital allocation line. The tangency point occurs at a standard deviation of the complete portfolio of 9.02% and an expected return of the complete portfolio of 10.28%. These are the risk-return parameters of the optimal complete portfolio with y equal to 0.41. We conclude that the choice for y, the fraction of overall investment funds to place in the risky portfolio, is determined by risk aversion, the slope of indifference curves, and the Sharpe ratio, the slope of the opportunity set. Non-normal returns. In the foregoing analysis, we implicitly assumed normality of returns by treating standard deviation as the appropriate measure of risk. As previously discussed, departures from normality could result in extreme losses with far greater likelihood than would be plausible under a normal distribution. Therefore, an appropriate extension of our analysis would be present to investors with forecasts of value at risk and estimated shortfall. Taking the capital allocation from the normal-based analysis as a benchmark, investors facing fat-tailed distributions might consider reducing their allocation to risky portfolios in favor of an increase in the allocation of the risk-free vehicle. Black swans, those rare but high-impact events that can result in drastic security returns, clearly would concern investors. Passive strategies in connection with the capital market line. A passive strategy describes a portfolio decision that avoids any direct or indirect security analysis. It involves investments in two passive portfolios, virtually risk-free short-term T-bills, or alternatively a money market fund and a fund of common stocks that mimics a broad market index. The capital allocation line representing such a strategy is called the capital market line. Historically in the US, based on 1926 to 2015 data, the passive risky portfolio offered an average risk premium of 8.3% and a standard deviation of 20.59%, resulting in a reward to volatility ratio of 0.4. Passive investors allocate their investment budgets among instruments according to their degree of risk aversion. We are at the end of session 2.3. After having carefully studied the slides and the relevant chapters in the book, please start with the review questions.